seeing you. This is very interesting. I want to get right up front so
All right.
I can get every word.
Which my husband's forget to show up.
I read your little
You're being
synopsis.
recorded at this point.
It's
FYI.
fascinating.
I tried to make it, a page turner. My summary. That's my
So,
defense.
when did y'all get in?
Well, I got here at 9.
Up here.
Oh, sorry, yeah.
But where did
Hello,
does it
Elon.
actually say?
Oh, you know.
When did you get in?
Very calm. Not stressed at all. Sorry, what?
You need anything?
Do I need anything?
So you haven't seen shit?
Why should you be stressed?
Oh, you did see
Yes,
shit?
Why should you be
yes.
stressed?
She had a dinner.
Uh-huh.
She had
Oh,
That's fine.
and you're here how much longer?
till Saturday morning.
You're leaving tomorrow and you're going,
So Saturday morning.
oh, Saturday, oh,
I
good.
think.
Huh?
I think.
Help.
No,
I'm not quite sure, but
you're being recorded at this point.
You should have a sign on the door saying you're being recorded.
There's a sign that
There is?
it's being recorded.
Okay.
I didn't put the sign, but the sign is there.
So I'm walking around my
Massachusetts is
sheet
all part of
and
the
knew that
consent
I,
state for,
so she
recording.
escorted me all the way from.
Yeah, but there you go.
Now he has a.
Fortunately, I was on the other side and someone saw me looking at my sheet wandering around this building is
Yeah, but let's face it.
rather beautiful, but not very.
That's gonna be a joke.
Not even ask like a maintenance person. So I can help you. But she walked me all the way over there right through the door.
Oh, that's
And
nice.
she knew, when I said Zelda, she knew, oh, yeah.
Oh, really?
Yeah.
Wow.
She was
Said
said,
long hair
yes,
in a green dress?
thing, so she said something about research team.
Okay, she was the one, I think she was the head of Zoe's research team. So I just ran into her. Did she meet you or no? She's a woman, she has like long, blonde, kind of curly hair and a green dress. We saw her here earlier, and I think she's the one that Zelda wanted as her thesis advisor. And then decided to take Serena on this woman, coach her.
This is recording,
Oops.
just in case you need to know that.
Just in case
So
someone speaks office here.
keep it clean, Karen.
Parce qu'on peut voir les juristes.
I mean, you need a very thick if you're gonna get all the frequencies in voice.
Yeah.
In fact, if anything, I worry they're not picking up.
Did you read through the summary so that you at least catch the
For life?
Okay, so that's long. The cake is a lot.
Zelda, would you know how to give your speech in French?
No.
She explains basically in your speech.
No. I mean, half of the words that define the concepts, I don't know how to pronounce
I
them.
know people know that.
RSI channels.
All right. How do you call a strongly Rayleigh measure in French?
What application?
Sorry?
How do you say a strongly Rayleigh measure in
Well,
French?
yeah,
Forcément rêvé.
See, that sounds stupid.
It sounds stupid in English too, just FYI.
Wait, so like right now, it would go and my sister.
They can all hear what you're saying.
All right.
You know,
Get out of
it
the
happened to me once. I prepared a speech in English. Once I prepared a speech in English.
I can tell you how many people are watching. There's only one person watching.
We have a German band here. It doesn't speak English, so could you give it in German?
Mom, where are you using the clicker? The clicker, the clicker. The clicker, the clicker.
Yeah, you know, you can clearly see what there's when you switch the transmitter on, there's when you start with the AES.
Yes, you actually.
Yes.
Because he shows the part you can't see.
That's all I want.
What is the quality of the?
When do I start thinking that my thesis is my name?
Actually feasible or is it like?
11:15.
Well, so they demonstrated it at 10 meters in Alexa. It's got 24 dB and 20 gains from TP Link to our
Half faith.
The other thing is you don't need all of this.
Yeah.
There's a lot of glare. Well, like right here, it's fine.
I mean, their threshold was keyword power.
I moved the settings a bit so you don't look like
You get
I'm never a weird color.
and the camera was shook.
And in particular, they do key recovery from sort of arbitrary random plain text.
So just that's it.
Well, yeah, but like, I don't know if you're familiar with the acoustic sidechain work by Daniel Jenkins. That relies on a crafted plain text.
Yeah, but anything you get back, you talk. Obviously,
For its time, the work
And
was
there is
groundbreaking
one
and
other
it exposed a
person
particular
that
configuration vulnerability where
my
basically
friend
you
on the
had,
vineyard.
I think it
As
was
soon as I get on
TTP
the
set up
boat,
with
he
your
sees that he's coming to
email
pick me
to
up.
automatically
Is with
decrypt
Okay.
emails to
So then you assume you know.
Exactly, so they actually did demonstrate
Camera
a
said we can
reasonable
right.
test.
Because if you haven't, that's
And so basically, one of the points of that paper was, well, A, you need to do this one. And B, that you probably shouldn't just set your client up automatically.
What am I supposed to do?
The automatic is not automatic. Those should be focusing on more important efforts. So we're going to.
I know those papers.
Really? Yeah, learn something new. Has absolutely nothing to do with it.
Actually, I
Have
don't
you
know.
used Netflix? Maybe if you come to Himalayas?
How did you know that's my next step?
It's again.
Well, no, I read that attention is all you need.
It's a.
No, actually, one of the Ashka! Hello!
I'm so excited.
So am I, but I'm not sure if it's good excitement.
Can you give you a high five?
Yes.
I would also be so fun, but I don't know.
You know. I'm not good at that, but it was not your part. Ooh. You say it's not that good, and then you add that your car, just add it to a picture.
Blissfully
What can I say? All right.
Happy the entire time. This felt great to me. I'm absolutely happy.
Negative events.
But yeah, it was, so you're not familiar with this JJ configuration?
I'm not supposed to,
Okay, well, so it was pretty funny, because he was like an undergrad teching on that.
Okay.
And decided to demonstrate that the scenario of getting a microphone close up to the computer was
Oh, yes, I'm familiar with that paper.
It'll be
by hiding the microphone in a
Yeah. Okay. So, yeah, so that, this extension, this is our extension.
Yeah, this paper is ours.
Okay.
Yeah.
There's also an option about EM, satellite on the board. There's some people claiming to do acoustics using Windows. So there's,
I mean, I would believe that you can get us talking through.
Yeah, that's
Demonstrating for-
Yeah.
No, it's fine. We're really excited.
Getting into the coil launch and reality.
That would seem.
It would take a very special
And there is an
basically, the bread and butter is DSC. This is for, reading this for a doctor project.
So which point do I start
We
supporting?
work closely with the we coach a lot of people. And we'll go on that.
Google's looking at
I didn't do it. That's a pretty easy solution.
Yeah, that's what they just try to see what they're trying to do. No, you know what, it's the search algorithm, complementarity. It's what it's network search. So basically, in every node, every event, values, what is complementary. Sorry,
Yeah.
so you know,
Well, I mean, that's sort of the basis of,
yeah, that's okay.
you know, taking advantage of it. I mean, I'm well familiar.
So basically, you know, you don't kick them out, you actually use it. It's beneficial. You download the article, you behave like your well, I guess that's sometimes. So it's really over. I mean, that's
I mean, the challenge, of course, is that every, well, you need every population.
you need people to sign up, ideally, anytime. You don't need to talk. I can get it all. Yeah, but you need very finely
Are you live streaming?
Yes.
Nice.
Well, I was attempting to.
Gotta be computer, yeah. Okay, that's a lot. Just
He's convinced all I have to do is like Twitter.
Can you do me a favor? Can I send you a too long to send things to check and I'm not sure if I'm seeing it fine because it's my account.
Oh, that's cute, but I have it now. How is it?
Hello, how's it going?
It's like, I'm fine. I jumped a bit. It was funny.
One more thing, sorry.
Is that seat next to you, Tucker?
No.
Alright, let's do that.
But don't turn any of the light on. Okay, that one's working?
Yeah, that one's great. I'm scared.
It's running on a delay.
Yeah, that's fine. It always has like a 30-second delay or something.
Probably just to make sure it's not I told you that
Sorry, was it?
You should send me the details as to when those are.
Okay, well, actually, it's like after the first day of vacancy, and then I plan to make trust
Okay. But you have bigger things to worry about.
Well, I am really looking for any strategy to do, right?
Okay, so whatever.
I was reading Mark's paper on like transmitted radio frequencies or whatever. Like,
Alright,
that sounds
we're live
nice.
What exciting weekend plans?
Going to Miami with my parents. Oh no, too much lights. Why is it decided to be sunny and too much lights today? I've already done moving some of the color. So I just want to make sure.
By the way, I heard you decided to sign up with Google.
Yes. My team is here in
Where is it?
Google Brain Team.
Oh, really? So you have like a joint audience?
Yes.
That's super cool.
Ouais. Qu'est-ce qu'il y a?
Non, juste là, je te dis après.
Non, mais dis-moi.
Tu reconnais pas les visages tout en fait.
Ils sont là-bas, ils sont là.
Non, mais j'ai compris.
De quoi tu parles?
Ils ressemblent pas du tout à ce que tu m'as dit.
Oui. Oui. Le jury bah, c'est eux deux. Et ah non, moi je sais. Bah, tu vois, c'est le mec avec qui je suis le mec qui est en train de parler, c'est aussi
So I took today off.
et puis Stéphanie, c'est...
Yesterday at 8 p.m., literally every work said it's like scheduled meetings at 8 p.m.
Mais ils ont dit ça, c'est pas
6 of them. And I was just like, guys, I just can't. No, I'm hoping to get talk. Like, go away. Look, nobody wants ever to meet with me for the last like month. Come on.
Je vais avoir une crise
Let's do
cardiaque.
that. And I was just like, everything in my calendar is off.
I'll still be around on Thursday night. They'll be around on Thursday night, not like maybe 10. This is the more pieces of that, this is the same having a job sucks.
Non, mais oui. Bonjour.
Salut.
Salut. Je sais pas que ça allait, c'est pas plus.
Mais il vient pas pour la cérémonie. C'est personne. La plupart de ces décès, il y en a 4-5 qui viennent.
Although I think that he didn't do very Mais en échange ici, on y passe 6 ans au lieu de 3. I usually like, keep happening. Maybe it's different what hopefully not it might
For some reason, randomly dropped.
I was not on YouTube.
Well, that's crowded.
I was Okay, I'll try to behave myself. Please do not touch the camera. Okay, sorry. This is not. I probably should have said. Okay, I'll go at the back.
He's the guy who does so much math. At his top.
I spent a long time trying to look at
Everyone just like
share, and I just couldn't figure it out. Bring it right. And that was just the easiest thing.
Yeah. Well, bon courage. Enjoy. Yeah.
That's, well, I see people are pretty enjoying the fruits of our labor. So it's my great pleasure to introduce to you Zelda Mahir, my very first PhD student at MIT. And there's many nice things I can say about Zelda. I'm going to say a few so that I don't put too much pressure on her. She has to display that in her talk. So, Zelda it's a very interesting story actually. Before we moved to MIT, Zelda had contacted me interested in exploring some projects in machine learning, and I had a bunch of things I was interested in talking about, so I just I think wrote back to her that let's talk about the project. And Zelda holds the distinction, I don't know if there's a counterexample to that in the room, but she holds the distinction, at least for me, for having the fastest paper a student has had with me. So I think when I communicated the project with her, we talked, and I think within, and she showed that my initial idea was wrong. She fixed it, came up with a nice creative idea, and within 1 week, I think we had solved the problem and were ready to submit to the ICML the next week. So that was personal best for me also that I've seen so far.
I have
So,
a manager.
and that was work actually on determinantal point processes, and it turns out that she has gone on and developed a lot of interesting work in that area. Some of that she will talk about today. And I have actually been very happy. Zelda is a very creative person, and one of the things, maybe her friends know that, those who have not worked with her may not know that, is if you want to get something to work, put her on that. And even in the face of stiff NIPS/NeurIPS deadlines, she has managed to, despite odds, somehow get things to work. And by putting in both creativity, mathematics, hard work, programming, hacker, coding, everything. We share a bunch of other things in that direction in terms of her non-academic interests like science fiction, etc. But I'm not going to diverge too much on that. And I'm actually really happy and proud to see her do her defense today, and now the stage off to her.
Thank you for the introduction. Thank you everyone for being here. And so I'm going to be talking, as you know, about the research I've done for the past 4.5 to 5 years for my PhD. And so this research has been mostly about the theory of negative dependence, and especially how we can use the theory of negative dependence to approach a broad class of problems in machine learning that require a model of diversity. So let me begin by actually giving you some intuition behind the concept of negative dependence. At a really high level, you have negative dependence when you sample multiple items at once, you're not likely to see similar items show up simultaneously. So it's a very trivial example. Imagine that you're picking balls out of an urn. One example of negative dependence could be you're more likely to see balls of different colors than balls of the same color. But negative dependence actually also arises in the real world. So the simplest example I could think of, which is an example that most of us probably lived through, is going to the movies with a group of friends. Now, as a group, you're probably going to want to sit far away from other people because you don't know them and you want to hang out with your friends. And so if I were interested in modeling the relative distances between groups of people, I would probably actually notice that if I look at two seats that are close together, they're very unlikely to be seats that are assigned to people in a different group, because these groups don't want to overlap, right? There's this repulsion effect between between different groups. And so this idea of repulsion is very characteristic of negative dependence. But it turns out that negative dependence doesn't just arise in the antisocial patterns of humans. They also arise in a lot of various natural phenomena. For example, if you're familiar with the Pauli exclusion principle, it states that you cannot have more than one fermion per quantum state. And so this, in physics, is a very fundamental notion of negative dependence, a very local and strong notion, where the presence of one fermion in the local state excludes any other fermion from being in it. And if you're more familiar thinking, for example, about biology, you can also see examples of negative dependence that arise in neuron activation patterns. Because some neurons, under certain conditions, when they fire, will keep other neurons from firing as well during a certain period of time. And very much like this phenomenon of repulsion, the idea of inhibition is also a very strong characteristic of negative dependence. So it turns out that machine learning also has its fair share of problems that require some notion of negative dependence. So as a running example throughout this talk, let's think about automatic summarization. Imagine that I'm going to give you one very large document, and I'm going to give you the following task. You're going to have to summarize it by picking sentences out of it and gluing them together. So this is probably not going to yield a very good summary, but if you did want to do as best as you can with this kind of task, you would want to pick sentences that are summarizing different parts of the document. You would want some kind of semantic diversity in the sentences that you've chosen. Once again, diversity, negative dependence. And for one final example, one of the most classical examples of negative dependence in machine learning applications is recommender systems. So imagine that you are working in a recommender setting, and I come to you and I tell you, give me information about bows. Without additional context, you don't know if I mean a bow tie, or maybe a violin bow, maybe I'm interested in playing the violin, or maybe I want to do some archery. So since you don't have the context that you need to answer this fully, you're going to want to pick a set of answers that, once again, is going to have this semantic diversity, to be sure that at least one of the answers will be relevant to my question. So these are only two examples in machine learning. The rest of this talk and my thesis has focused on how the theory of negative dependence can provide a framework, a theoretical framework, to think about these problems. Okay, so the outline of this talk is the following. I'm going to begin by actually defining formally the mathematics that underlie the theory of negative dependence. Once we have this background, I'm going to discuss a very classical model of negative dependence in machine learning, which is determinantal point processes. And I'll conclude by talking about whether or not we actually have the right model of negative dependence in machine learning, and propose a partial solution to this in the form of exponentiated strongly Rayleigh measures. But let me begin by actually talking about the theory of negative dependence. Okay, so in all these examples, I've been talking about the idea that you're sampling multiple items and you want them to be different. So the formal context for this is going to be a distribution over sets of items. So you have n items, maybe n sentences, and you want to sample a subset of them by a distribution mu, which is going to provide you with your summary. So the most straightforward way of modeling this concept of negative dependence is by what's called pairwise negative correlation. And here's the intuition behind it before I actually talk about the inequality itself. The idea is, if you picked item I, if you picked sentence I, you should be less likely to also pick sentence J, because there's going to be some semantic overlap between those two sentences. So this inequality here, saying, so mu of I and S, the probability of sampling point I, according to your distribution, should be greater than the probability of sampling that point if you already know that you sampled point J. So this is a very natural definition of negative dependence. But maybe it's somewhat limited in how far it can take you, because if you look at what it's actually telling you, it's only talking about interactions between pairs of points, between pairs I and J. So we might actually want a stronger notion of negative dependence, be able to kind of narrow down the framework we're thinking about and get better properties. So a natural way of thinking of extending this negative dependence is by asking this inequality. Oh, first, actually, let me say this. We're going to rewrite the inequality by applying Bayes' rule. So this new equality is equivalent to the previous one. It's just going to be easier to manipulate. So an easy way to ask to extend this inequality is to say, well, let's have it hold not over pairs of points, but over arbitrary sets. And even further, we might also ask, well, actually, how about we have it hold for functions over arbitrary sets? And so the way to do this is first to, once again, rewrite the inequality. Again, this new inequality is the same as the one above, but we've rewritten it in terms of expectations. So here xi and xj are the random variables corresponding to the events. I picked element I picked element j. And so once we have this new inequality in terms of expectations, to extend it, all we have to do is rewrite it with these functions over arbitrary sets. So now we have a new concept of negative dependence, a new characterization, commonly known as negative association, and it is much stronger than the previous one. It applies it directly. We created it to be stronger. And so with this narrowing down of the concept of negative dependence, we have a better framework to think about. So we now have two characterizations of negative dependence, and we're actually going to need a third, which is called loxomodularity. And unfortunately, in the scope of this talk, I don't really have the time to discuss why loxomodularity is a good notion to have in negative dependence. But at least in machine learning and optimization, we know that functions that are submodular or loxomodular have nice optimization properties we can take advantage of, which is, I think, all we really need to do for the time being. And so now we have these three characterizations of negative dependence, and they all come with nice properties. So the problem, before we talk about the properties, the issue we're going to have is that even though we have this nice implication between negative association and negative correlation, we're actually not going to have any connections between loxomodularity and the either two. And the problem is, this means that we're going to have to pick and choose which characterization we're working with when we're thinking about negative dependence. And that's unfortunate, because all of these characterizations have various properties that we would like to take advantage of at the same time. For example, negative association can be shown to yield fast sampling algorithms, and fast sampling algorithms mean efficient applications. And loxomodularity, as I've already said, leads to nice optimization properties over your function. And so we would like to be able to take advantage of all of these, but the problem is we're actually in this diagram, right, where we have the pairwise negative correlation and inequality, the first one we started with, negative association and loxomodularity, and we would like them to all be concentric, but they're not. And so if we wanted to actually apply, this theory for anything and be able to take advantage of these properties, we would like to lie here at the intersection of all three, where we'd have the nice optimization properties, we'd have fast sampling. And so for a long time, the research in negative dependence worked on characterizing a subset that would lie at this intersection. And so this is going to be the topic of the next couple of slides, which is in 2009, Borsia, Brandon, and Leggett managed to characterize strongly Rayleigh measures, or SR measures, which are going to lie at this intersection. All right, so now for some math. I'm going to actually need to talk about strongly Rayleigh measures for a bit, so I'm going to introduce them, but hopefully I'll be able to clarify why this notion is going to be important. So once again, we're thinking about measures, probability measures over subsets. And so we're going to think about, for a second, to go to the definition of strongly Rayleigh measures, we're going to move to the world of polynomials. So any measure over subsets admits what's called a generating polynomial, which is I've written here as G mu. And the way you obtain such a polynomial is by evaluating your distribution mu over all possible subsets. That gives you coefficients to the polynomial. And it has n variables corresponding to the n items you could be taking, which are complex numbers. So moving back to probabilities. A probability distribution over subsets is called strongly Rayleigh if this generating polynomial cannot be equal to 0 when the imaginary parts of each of the variables are strictly greater than 0. Now, when I first saw this definition, it was not entirely clear to me why this is going to yield negative dependence properties. And not only is this not very intuitive, it's also not very easy to understand, to analyze where the zeros of polynomials lie. So this is also a characterization which is very hard to work with in a lot of settings. Fortunately, in the same paper, Borsia, Brandon, and Leggett showed that we have this alternative characterization, again, through the generating polynomial of the measure, saying that a measure mu is strongly Rayleigh if this inequality between partial derivatives is true. And so this inequality has to hold for all real numbers. So again, you might be thinking, well, how does this give us any negative dependence? So I'm actually going to spend a few minutes and try to show to you that with this very simple inequality here, we can actually recover the first inequality for negative dependence that we started with. So let's see if I can pull this off. What we're going to do is we're going to evaluate this inequality at the vector of all ones, and everything is going to happen very nicely. So our generating polynomial, if we write it out, just rewriting the definitions, is the sum over all subsets of our our distribution at each subset, and then the random variables that are in the subset. So for all k that appears in our subset, we have these k's. That's just a definition. All right, so let's take the partial derivative according to I. Can you all see what I'm writing? All right. So what's going to happen? This term in the sum is only going to stay if item I is in the set, right? So we're only going to take sum over sets that include item I. And then this term, since we're evaluating it all ones, is going to be equal to 1, right? So here we have, this is a rephrasing of the partial derivative at 1. And if you think about this, stop thinking about polynomials and go back to probability distributions, this is just a marginal probability of you choosing item I, right? So this is actually the probability of I being in your set. All right? So now, let's rewrite this inequality. This inequality tells us that the probability of picking our point I times the probability of picking our point j is going to be greater than the probability of picking I and j by the same reasoning, times the vector g times g at the vector of all ones. Right? I haven't done anything fancy. And it turns out, if you evaluate g at all ones, again, these terms disappear, so you just have this sum, which is just a partition function of our distribution. And since it's a probability distribution, it has to sum to 1. So this is the inequality you end up with, where basically this is equal to 1. And if you recall, this is the first characterizations of negative dependence we started with. If you pick item I, you should be less likely to also pick item j. So hopefully you have at least some understanding of why we're going to care about this notion of strongly Rayleigh measures. And especially this second, I'm not going to really use this characterization for the second talk, but if you want to work with strongly Rayleigh measures, it's important. So not only do we recover the pairwise negative correlation that I just did on the board, as I mentioned, you do light the intersection of our Venn diagram. So you also have logs of modularity and negative association. So even though the characterization of pairwise negatively dependent measures may be a bit difficult, especially strongly Rayleigh measures, they actually appear in a lot of common scenarios. The simplest strongly Rayleigh measure over subsets is going to be what happens when you pick items independently from each other. Right? So you just build your set, picking points one after the other without caring which ones you've already chosen. A second way of doing it. Okay, if you're picking points, if you're picking balls out of various urns, the probability of seeing an empty urn, if you've already seen an empty urn, is also actually strongly Rayleigh. The probability distribution that's induced will also be strongly Rayleigh. If you like thinking about graphs, you can actually show that the uniform distribution over random spanning trees of a graph is also strongly Rayleigh. As another example, maybe you care about doing variance reduction or experimental design. If you do, you may have seen a probability of this form, where ek is an elementary symmetric polynomial. And such distributions, which are basically picking points based on the columns of a matrix that's already given, is also strongly Rayleigh. I won't have time to talk about it in this presentation, but feel free to ask me questions about it later. And finally, determinantal point processes. So determinantal point processes pick points according to the determinants of submatrices. And I'm actually going to spend the next part of this talk discussing them in depth. And so to recall, you have to remember that they are strongly Rayleigh. Okay, so let's move on to the second part, determinantal point processes. To define a determinantal point process, you need one specific thing. So recall we're thinking about distributions over subsets of a ground set of n items. Maybe, again, these are n sentences. And so you have the determinantal point process, or DPP, if there exists a matrix L, which has to be positive semi-definite and is size n by n, where n is the number of elements, such that for any subset that you can pick, the probability of observing it under your DPP is proportional to the determinant of your matrix L indexed by your subset. So what does this mean? This really simply means that if your set is items 2, 3, and 4, so you're trying to evaluate the probability of picking sentences 2, 3, and 4 for your summary, the way to evaluate this probability is to look at your large matrix L, and then simply look at the intersection between rows and columns 2, 3, and 4, and look at the determinants of the smaller submatrix you've just obtained. That's really all that's happening with the determinantal point process. And it turns out, I've already mentioned this, but just to reiterate, they are strongly Rayleigh measures. So before I start talking about maybe the concrete science and contributions behind them, let's see what they actually do. So a standard example for determinable point processes is looking at what happens if you sample over the unit square. So here we're going to look at the unit square, which we've created a grid over, and we're going to look at different ways of picking points over this grid. The simplest way of doing this is to say, okay, we're going to pick points independently from each other, one after the other, uniformly at random. So for example, you start with this point, and then you say, okay, forget you picked it, and pick the next point, and do this as many times as you want. The problem with this approach is that as you do this, since you don't care about points you've already chosen, you may end up with areas that are entirely empty, and also with areas that comparatively have been sampled from much too often. The idea of negative dependence is, hopefully, if we manage to characterize the fact that we want negative dependence between points that are close together, we should manage to get a more uniform spread of points. And if you do this with a determinable point process, if you pick the kernel appropriately, that is exactly what happens. Since two points that are close together are unlikely to co-occur, you end up paradoxically with points that are distributed much more uniformly over the unit square. So this is the first concrete explanation of what a determinable point process does. This is, if you remember nothing else, this is an illustration you should keep in mind. And so I would argue that one of the main strengths of DPPs is actually that they have this very nice intuition that you can think about when you're applying them to various tasks, and that makes them very interpretable and very easy to leverage in a variety of applications. So let's talk about this intuition just for one slide. Let's say that you have, again, your kernel L, which is what defines the similarity between points. And imagine that you can rewrite it as the following product, where phi here is probably, in applications you care about, going to be a feature matrix, a feature representation. So the probability of picking any set S, which is given by this formula, can actually be related to the volume spanned by the vectors corresponding to the points you've picked. So what does this mean? If you look only at the probability of picking 2 points, points I, points j, sentences I, sentences j, the probability of picking these 2 points exactly is actually going to increase as the area here, the volume in 2 dimensions, increases as well. So there's 2 ways of making this volume grow. The first way is to say, okay, we're just going to take our vectors and we're going to stretch them out. And this obviously also increases the area that's spanned, right? And so this is an operation that doesn't look at interactions between points. You're just looking at vectors, stretching them out. The second thing you can do is increase the angle between the vectors. And here you do care about interactions between points. You're increasing the diversity by increasing the angle between points. And so this is the very simple and nice illustration of why determinable point processes are able to do this trade-off between quality of the points you're sampling and the diversity that you care about for negatively dependent applications. All right, so now let's talk about using determinable point processes in machine learning. I have, as Sarit mentioned, spent a lot of my master's and PhD thinking about determinable point processes, and so have a lot of other people. And so I would argue that you can broadly classify applications of DPPs in machine learning in 3 broad categories. The first question you can ask is, how do I actually choose the characterization of my DPP? What should this matrix L be? So as part of my master's thesis, I looked at a fixed point method. This is the paper Sarit mentioned, actually, to learn the kernel L. More recently at AI Chats with my collaborator Mike Gartrell and Sarit again, we looked at incorporating into the learning problem knowledge of subsets that are not diverse and whether or not this can help us learn the kernel better. And finally, one of the problems with DPPs, which I'll actually get into in a second as well, is that operations over DPPs and algorithms for DPPs tend to be somewhat costly. So for the learning problem with Street, we looked at what kinds of structures we can impose on the kernel in order to have these algorithms be more efficient. And in practice, we showed that imposing a product for product structure is one such way of having faster algorithms. So now, let's say we have our kernel. We know how we're going to parameterize negative dependence. Now what we want to do is actually generate samples from it. And so as I've mentioned, operations over DPPs can be quite costly. In practice, if you have n items you're sampling over, they tend to grow as n cubed. And that's very bad for applications in practice. And the n cubed cost comes from any operation you would actually want to do over the kernel. If you want to invert it, if you want to take its determinant, or if you want to eigendecompose it, you're going to pay an n cubed cost. So for this part, we showed actually, again, in this previous paper with Sarit, that a chronic structure also speeds up sampling algorithms. With my collaborators at Google, Jenny Gillenwater, Alex Kalissa, and Sergey Vasilitsky, we looked at a pre-processing step that creates a tree over all possible items, and based on this pre-processing, you can then do sublinear time sampling over a broad class of determinant point processes. And finally, this summer, with Stanislav Vanya and Jasper Snowick, I worked on whether or not we can use neural networks to approximate samples from a DBP and obtain samples much faster. So, okay, now we know how to sample from a DBP and we know how to choose our DBP. All that remains to do is to actually use it in machine learning, right? So for applications in DBPs, these are only mine, there are of course many others. Again, as part of my master's thesis with Sarit, we looked at using determinant point processes for neural network pruning. The idea here being that you're going to use your DPP to tell you within a layer which neurons are doing diverse computations. And you're going to remove all the other ones. And the ones that remain, since they are diverse, are going to be able to reconstruct all the information you removed. And so you end up with a much smaller network with the same computational ability. As I've mentioned earlier, recommender systems have many requirements for negative dependence, and in particular, determinant point processes have been used in a lot of cases for this. So again, some previous papers touch on that. Classical application of determinant point processes. And so in kernel reconstruction as well, kernel reconstruction, which you can kind of think of as another way of doing the same class of problems as neural network pruning, you start with a large model and you want to store only part of it on disk. And it turns out that querying a determinant point process and asking it which parameters to store is also a good way of approaching a certain class of problems in this area. So I'm going to spend a few minutes talking about these applications, and in particular, how using neural networks, generative neural networks to create DPP-style samples can be used for these various applications. So, just to reiterate, there are many applications of DPPs in machine learning. Neural network pruning, kernel reconstruction. In 2017, Cheng Zhang and her collaborators looked at using determinantal point processes to choose mini batches and stochastic gradient descent, which is the standard algorithm to learn machine learning models, and in particular neural networks. And very recently, or somewhat recently, there have also been investigations into using determinantal point processes for fairness. The idea being that the diversity of the DPP is going to provide you with the fairness that you care about for your application. The problem with this is that a lot of these applications, and in particular the mini batch selection one, would be useful for cases where you're actually using neural networks. And neural networks require very large data sets to train. And they still end up being efficient because they can take advantage of very fast matrix multiplication and hardware accelerators. But DPPs cannot. So if you add a DPP into the mix, if you use a DPP to sample a mini batch, for example, you're going to introduce a very bad bottleneck to the process. And so this means that this has actually impeded the applications of determinantal point processes to a lot of applications in machine learning, because they might be the right model, but they're just too slow to use. And so this motivated our work with Stanislav Vanya and Jasper Snowick on using this fast neural network to generate the samples. Because if we already know that neural networks are fast, they have all these accelerators and fast matrix multiplications, maybe we can actually use them to approximate a DPP that would solve all of our problems. So, why might this actually work? We're going to assume that we're in the following setting. We're going to train a neural network offline, and we can spend as much time as we want, reasonably, to do so. What we want is to be able to generate samples from our DPP-like network as fast as possible during applications of it, so maybe when we're generating mini batch samples. But we can afford to spend as much time as we want during training, and that means that as we're generating training data, which we're generating from the true DPP we're trying to model, we can spend time getting those samples, which are slow. And so we can actually generate as many as we want, which is a very good setting to be in with neural networks because they are notoriously data hungry. Secondly, and this is very specific to the sampling algorithm for DPPs, remember the setup is you're generating a sample from the true DPP and then using it to train your neural network. When you generate that sample, the standard algorithm to sample from a DPP actually builds the set sequentially. So you start from the empty set, sample a point, add it to your subset, sample the next point until you sample as many points as you want. And so if you actually look at this in the framework of generating training data for a neural network, each time we sample a set of size k, we've actually generated k smaller subsets that we can use during training as well. So we have this very nice augmented data set, in a sense, of the trace that we use to generate the sample. So we know that hopefully things should work out in terms of the training setup. It turns out that you actually also have a theoretical guarantee that argues for such an approach. And in practice, what we showed is that under certain training assumptions on the data set and the training procedure, you can actually inherit important characteristics of the determinable point process in your neural network. Specifically, if you can bound this term here close enough to 0, where this term is the true probability of the determinable point process, the distance of that probability to the probability that you're approximating with the neural network. If you can bring that close enough to 0, the neural network's probability is also going to be loxy modular. And so this, if you recall, loxy modularity is one of these 3 characterizations we cared about in negative dependence. So it's telling us that we're going to recover at least some amount of negative dependence in our generative model, which is a very reassuring thing to know. So we now have a justification for our setup. We have some idea of why it might work, both theoretically and in practice. All really that remains to do is to see how we're going to approach this problem. So here's the architecture that we're going to use, the neural network we're going to use to generate samples. We're actually going to emulate the standard sampling algorithm from DBP. So let's say that you're sampling sentences to create a summary. You start with, at the beginning, you sampled no sentences at all. So to your neural network, you're going to give the empty set. And then you actually have to tell it what it's summarizing. So you're going to give it a representation of all n possible sentences you could be choosing from. So it's going to be this matrix 5. And into this black box, probably, these 2 things are going to go through a certain number of computations. This is going to be the neural network. And what we're going to ask is we're going to ask it to output the probabilities of sampling any of the next sentences. And so from these probabilities, we sample a sentence I, and then we repeat the procedure, just like a determinable point process actually would. And so if you actually go back, remember that what we said is that if we bound this term close enough to 0, we actually have loxy modularity. And so this is going to be the cost function we're going to use to train our neural network. We're going to ask for these, our cost function is going to be the distance from these probabilities generated by the neural network to the true probabilities from the DBP. Again, we can afford to compute all of these during training because we've decided we're doing training offline. And so if you repeat this process k times, you're going to end up with a set of size k, and everything should be fine. So now let's look at various applications. We have an architecture, we have a justification, but we really need to know if this works in practice. So first application we looked at was data summarization over every machine learner's favorite training set, which is MNIST. So the task is the following. I'm going to give a neural network, our neural network, a subset of images. So MNIST is images of digits, handwritten digits. I'm going to give it a subset of, or a large number of images, and ask it to return a representative subset of these images. And our goal is to see how representative the data set, the subset is going to be. So here's what it looks like. In this task, we trained over all images of MNIST in the training set, but only asked it to summarize 7s. So the numbers up here, negative log likelihoods, are actually telling you how good the subset is according to the true DBP. So the smaller the better. Just remember that. So the first way we can sample things is, again, the simplest way, just pick the points uniformly at random. And so here you have, 7s. They're 7s. There's not really much more I can say about it. And the negative log likelihood is 32. It's going to be important because it's larger than the next ones. Now, if you sample from our neural network, you can do so either just by sampling from the probabilities or by taking a greedy mode. You see that you start, first of all, the negative log likelihood goes down, which is a good sign. It's quantifying how good our parameterization actually is. And we also start seeing more diversity in the actual 7th that we're looking at. For example, here you have a 7 that actually has a horizontal bar. You also, I would argue, have 7s that are only 7s because we're told they are. And finally, of course, if you do sample according to the true DBP, you also have this kind of diversity, and you have even worse 7s. So this is an illustration. The paper itself has more quantitative investigation into the results. Feel free to report to it for the error bars. But this application is a very novel application of determinable point processes. To our knowledge, there hasn't been really other work in using DBPs for data set summarization. So we also looked at another downstream task for DBPs. So recall how I mentioned that DBPs can be queried to reconstruct a kernel? The idea is the following. You've learned, maybe through ridge regression, a very large kernel that you're going to use for predictions. Not a DBP kernel, a standard machine learning kernel. Now, you don't want to store all of it on disk because it's very large. So what you can do, according to the Nystrom method, is from this kernel, select a few columns and only save those columns. And if you actually need to use the kernel at any time, you can reconstruct the kernel based on only the columns you saved by the following formula. The formula isn't very important. What you need to know is that the columns you choose are going to determine the quality of the reconstruction. And so it has been shown previously that choosing these columns appropriately leads to better reconstruction. In particular, determinant point processes are a very good way of doing so. So what we did is we said, okay, we're going to use various sampling algorithms from DBPs, either the standard DBP sampling algorithm, our neural network, and an approximate sampler called MCMC, and see how well the reconstructed kernel actually works for the task it was made to. So we learned a kernel for regression, for predictions on a data set. Select columns from it, store only those, and then reconstruct the kernel based on them, and see how well the kernel predicts on its original task. So here you have the mean square error. So the bigger it is, the worse the kernel is performing. And on the x-axis, you have how many columns you've allowed yourself to keep. The different lines show the different ways of actually picking these columns. And so as expected, across all of these lines, you actually see a decrease. The more columns you keep, the better your approximation. Unsurprisingly, the error goes down. And so what you see is that the DPVNet mode in particular does follow this trend, and it's very quite close to the determinant point process itself. So we know that it performs well enough, or at least well. It's not entirely as good as the determinant point process. That's the price we pay for actually using an approximation. But it works well. The second graph shows what we actually started out to do, which is it shows that our neural network is much faster when generating these samples compared to any other way of generating DBP samples. And this was really the crucial task, right? Because we want DBPs to be able to be used in downstream applications without creating a bottleneck. I'm sorry, the sunlight keeps changing, so it's not easy to see. So what you can see, so unsurprisingly, the DBP sampling algorithm, as I've mentioned, is very slow, and you can see that reflected in this dramatic increase as you increase the number of columns that you're picking. And even the MCMC sampling algorithm, which I haven't described but is very efficient, is an order of magnitude slower than sampling from the DBP nets, which is really what we set out to do. All right. So I have told you about determinant point processes. I have told you about the theory of negative dependence and how it can be used. So now here's the third part of the talk, and here's maybe the main part of the talk. Although negative dependence is a very important concept and is applied in a lot of different settings in machine learning and in the real world, the current definition of negative dependence measures, strongly Rayleigh measures, those are very useful for doing the mathematics of negative dependence, and they have very nice properties, but when we're actually caring about applying them to variety of tasks in machine learning, we're going to need something else. We don't necessarily have the exact right way of thinking about negative dependence yet. So the last part of this talk is discussing how we can get closer to the negative dependence we actually need for applications in machine learning. All right, so let me start with some observations to motivate what I just told you. We know that strongly Rayleigh, I'm telling you, that strongly Rayleigh measures emit fast sampling algorithms. We saw that neural networks can emulate some of them, and in general, they do have tractable approximations for most cases. Maybe not so that you can throw them directly into a neural network, but they're close enough. So that's good. That's something we need for applications of strongly Rayleigh measures and negative dependence in machine learning. The problem is, the notion of negative dependence, this repulsion strength that we get from a negatively dependent measure, is not something we can control. And in applications of machine learning, data is never as clean and pretty as the mathematical world, right? Data is messy, and we're going to need to calibrate our model to follow the diversity that we need for our various applications. And strongly Rayleigh measures do not make that possible. So in an ideal world, we would want to be able to do both. We would want fast sampling algorithms, fast learning algorithms, but also, in a sense, a knob that we can tune that increases the strength of the diversity, that increases the strength of the repulsive forces, or alternatively, diminishes them and tempers them down. So the idea of this talk, or this part, is that we can actually do this in a very simple way. And the way to do this is to build upon strongly Rayleigh measures, which we know already have these fast sampling algorithms, and add this knob that we want that controls the diversity. And the way we're going to do this is kind of spoiled by the title of the slide, actually, is with an exponent. So what we're going to do is we're going to create an exponentiated strongly Rayleigh measure, ESR, by starting with any standard strongly Rayleigh measure and adding this hyperparameter p, this exponent. And this exponent is going to be the knob. So why does this work intuitively? Let's say you make p go to 0. What you're doing is you're actually squishing your probability measure in a sense. You're making it go close to uniform. And once it's completely uniform, you have no preference for diversity. On the other hand, if you make p go to infinity, the mass of the probability distribution of your ESR is going to be all at the mode of the distribution. And so here you have a full preference for diversity. So intuitively, this should do what we think an ESR should do. We should have this knob. So first, let's begin by verifying this in practice on a toy example. So here we're going to look at a toy example of outlier detection. Here's the idea. You have a data set, points drawn according to a Gaussian, and then I added manually some points that don't quite belong with this distribution, right? And so the determinantal point processes and strongly Rayleigh measures pick diverse things. So if we choose these points according to a DPP, we should be more likely to pick the outlier points than the other points, on average. So what I've plotted here, the color scheme tells you how often points have been selected. The darker blue they are, the less often they're selected, and the brighter they are, which again hard to see the light in here, the more often they've been sampled. So you can see that already with a standard DPP with p, so this is an exponentiated DPP with p equal to 1, so it's just DPP. You see that we're pretty good at detecting the outliers. So what happens if you make p go to 0? So the difference, you can really see it when you look at the outer ring of this circle here. You can see that these points have become much lighter, and so they're being sampled more often, even though they're not outliers technically. They do belong to the true distribution. And you're making p decrease, which, as you may recall, means that you're making the distribution go closer to uniform. So this is doing what you expect it to do. And so the next question is, well, what happens if we increase p, if we start increasing our preference for diversity? And so once again, if you look at the outer ring, you see that we're not sampling from it at all anymore. We're only sampling these outlier points. And so this confirms our intuition that we have a strong preference for diversity, that we are picking out only the outliers. So now we know that our intuition towards this knob, this hyperparameter p, is good. So now let's see if we can actually use DPPs, or if we can actually use exponentiated DPPs and other strongly Rayleigh measures. The thing is, I've actually lied to you a bit. I hid the difficulty. When we define an exponentiated strongly Rayleigh measure, here I'm hiding a lot of what's going to be the problem. The true way of writing this out, not as a proportionality, but as an equality, means that you need to introduce, since we're thinking about probability distributions, you need to introduce the normalization coefficient, because you need mu to sum to 1. And of course, this is where everything is going to start getting more complicated, because it turns out that computing this normalization coefficient, the CP, is NP hard. So we're going to need to find a way of avoiding this in practice. And just to be clear, computing this CP is hard even in very simple settings. As soon as p is different than 1, you're kind of lost. The good thing is, remember how we have fast sampling for strongly Rayleigh measures? The idea here is going to try and take advantage of this fast sampling and recover fast sampling for our ESRs as well, without having to even ever compute this normalization coefficient. So here's a very bared down algorithm. I've hid all of the things that you would need to actually apply it, but the idea comes through. So this is an MCMC sampler, and the way it works is you're going to have a distribution which you can sample from easily, which is going to be mu, right? Mu is strongly Rayleigh, so we can sample from the past. And what we're going to do is we're going to draw samples from this easy distribution, right here. And then, as many times as necessary, we're going to switch this one by looking at this ratio of probabilities. And since we have a ratio, we actually don't need to look at the normalization constant anymore. And so here, we have hopefully a fast algorithm. And as I mentioned, we don't actually need to worry about the complexity of sampling from mu, since we know that as a strongly Rayleigh measure, it does have fast sampling. The question is, how many times do we actually have to run this loop, right? Like that's the actual difficult question. So the way that people evaluate MCMC algorithms, sampling algorithms like this one, is exactly by looking at the number of loops we need. So it's called the mixing time, technically. And what it is the number of this tau s of epsilon is the number of times you need to run the loop so that your approximate sampler utility is close enough in total variation to what you actually want to be sampling from. So what we want to do is to upper bound this term. The smaller it is, the faster our sampler. So as a specific instance of the more general theorem in our paper, we can show that this term is upper bounded by the following expression. So let me go through it with you for a second. We have a log of 1 over epsilon, so epsilon is how close we actually want to be to our true distribution. And this log of 1 over epsilon is very standard for MCMC sampling algorithms. The second part is more interesting for our application. First, we have a dependency on the set that has the smallest probability according to our proposal distribution. And that, in a sense, is reasonable because the set that's the least likely to be sampled is the one that's going to make our life complicated. The second part of the dependency is the distance from p to 1. So p is our knob that we're turning. And it's it's unfortunate that this dependency exists, but it's very reasonable to see. Because think of it in this way. If we didn't have a dependency between p and 1, if we could just make p go to infinity and not have to pay a price for it, we would have a fast sampling algorithm that would give us the mode of any distribution. And we're pretty sure that that should not be possible. So in practice, it is at least reassuring to see this term appear, where the further away you are from your distribution, the further away p is from 1, the worse your sampling time is going to be in the worst case. Now, let's go back to our favorite application, which is kernel reconstruction according to the nicer method, and see if adding this new knob and using these samplers, we can actually perform better than the current results. So once again, we're looking at the same task. We're looking at the test error of a kernel that we've shrunk using various sampling methods to choose the columns, and we're looking at how well it actually predicts on the true task. And so this time, we're not only looking at the DPPs and different sampling methods, we're actually looking at different algorithms to choose the columns we're going to keep. So here you have on the left the uniform method, which, as expected, is not going to be very good. Leverage sampling and regularized leverage sampling, which are standard approaches for this task. The usual DPP, and then exponentiated DPPs when you make p go closer to 0, equal to 1/2, and when you make p go to 2. And so what you see, so exponentiated DPP with p equal to 2 is the one we're going to care about, it's the line in orange. And what you see is that across all of these data sets, it does perform better in test time than all of the other methods. And in particular, it performs much better when you're picking very few columns. And this is the regime we really care about, because we want to be able to prune our model, our kernel, as much as possible and maintain modeling ability. So what we see is that having this additional way of tuning diversity is very useful in practice for applications, because the applications don't have, the negative dependence that they have is not exactly strongly Rayleigh measures. It's a very characteristic of their own problem. All right, so let me close the loop on this talk and go back to what we started with. Remember how I talked about this intersection between the various ways of characterizing negative dependence? I told you that strongly Rayleigh measures are nice because they do lay the intersection of all three ways we would care about. What I haven't told you is what actually happens once you add this knob, once you add this way of tuning diversity. What happens to the negative dependence properties? So here are some things that you can prove. It's very easy to show that our exponentiated strongly Rayleigh measures remain log modular. It's a one-line proof, really. However, you do not maintain, your strong exponentiated SR measures will not remain strongly Rayleigh in the general case. By adding this knob, you've lost some of your characterizations. You've gained the tuning ability. However, interestingly, although this is kind of more of an artifact than anything else, you can actually show that some exponentiated SR measures will remain SR in non-trivial cases. And without going into too much detail about what non-trivial means here, let's just say you're not allowed to choose p equal to 1, which means you just will have a strongly Rayleigh measure. And you're not allowed to make p equal to 0 either, because that's just uniform distribution. So you can actually derive some more complex distributions that, as you move p away from 1, remain strongly Rayleigh within a certain interval. And so what we have, at least in the current state of our knowledge, is this location for exponentiated strongly Rayleigh measures, where we have lots of modularity. They include strongly Rayleigh measures just by putting p equal to 1, but the other characterizations are still, there's still work to be done, still some open questions. All right, so this closes the loop, and let me kind of provide a zoomed out summary of this talk and what my thesis has been about. At the current point in time, we have a very rich theory of negative dependence. Mathematically, for the past decade, people have been thinking about it and developing very nice results and interesting theorems. Simultaneously, or maybe somewhat more recently in the past couple of years, in machine learning, we started to see many different applications of strongly Rayleigh measures to machine learning. People have realized that determinant point processes are good for sampling the Nyquist method, that volume sampling is useful for variance reduction in optimal design. But these applications are very punctual. People know that one thing works well for this scenario, another one works better for the other scenario. And we haven't really had, at least to my knowledge, the realization that the reason these things work is because these models are negatively dependent and because these problems model negative dependence. So the goal of my thesis is to provide one of the steps toward thinking about machine learning problems within this new framework of negative dependence and providing a more theoretically grounded way of approaching a broad class of problems by connecting the world of the mathematics of negative dependence to the actual applications that we care about in machine learning. So for this, I've done, my contributions kind of break into two parts. I've worked on efficient algorithms that allow for fast sampling and fast learning of negatively dependent measures, which makes them actually tractable for machine learning applications. And as I just talked about, I've worked on how we can develop a theory of negative dependence that is very specific to the kind of problems we face in machine learning. So at this point, as I said, this is just a step in this direction. There's still a lot of things that can be done and a lot of areas that can be explored with the concept of negative dependence. One of the most I don't want to say, it's not going to be simple, but an obvious choice of directions for negative dependence in machine learning is reinforcement learning. And the reason is because reinforcement learning cares a lot about the trade-off between exploration and exploitation. And when you think about exploration, you're looking at which trajectories are going to give you a high reward. What you want to do is you want to explore a space and find the right locations in as few steps as possible. So you want to pick a diverse set of locations to explore which you believe are going to yield positive rewards. And the same general idea, hyperparameter space exploration also is going to have these same kind of problems. If you want to find the parameters for a neural network that has way too many hyperparameters to tune, you want in very few experiments isolate the regions which you should focus on that are going to yield a small loss once you've trained your network. And so once again, this trade-off between quality and diversity, the quality of the hyperparameters you're looking at with the diversity of the spaces you've explored, is a very natural way of thinking about this problem. Moving slightly away from this, I mentioned earlier that there's been this work by Chen Zhang on using determinant point processes to sample mini batches when learning various machine learning models with stochastic gradient descent. I believe that there's probably still some work to be done in this area, that there's still some paths that can be explored, and this is a very important path to explore because stochastic gradient descent is such an important algorithm today for machine learning. And finally, I also mentioned very briefly that there's a somewhat intuitive relationship between negative dependence and problems of fairness in machine learning, where you think that maybe the diversity that you obtain with negatively dependent measures may, if you have the right characterization, yield a way of thinking about fairness that corresponds to the way that you want to think about fairness in this given setting. Which is already something that's led to a lot of debate in machine learning. So with this, I'm concluding my defense. I have a lot of people to thank. I'm not going to make you sit through the list of people, but if your picture's up here, thank you for your help, your support over the past 5 years. If your picture's not up there, I'm sorry, but I thank you anyways. And this concludes my talk.
So we have time, the floor is open for questions from the audience. So go ahead with any questions you have. Yes?
So you were showing the mean square error as a function of subset size, and I was noticing that for DPP it went kind of like this. What was the reason for it? Was there a
So
reason
we
for
think
that?
it's an experiment. So you're looking, this would be the slide. Oops, sorry. Right, this one. So we think that's actually just an experimental artifact because there's a lot of randomness. We have this very high error bars. This is on one data set. If you look at other applications and with the ESR applications across data sets, that doesn't happen as much. This might just be because we're subsampling from the set itself, and so we're introducing additional variability. Yes.
DPPs are operating over discrete support, right? So is there a continuous analog?
So there is a continuous analog of determinant point processes, which I haven't really worked on. But you can actually, there has been work, I think by, if I remember correctly, Lavoisier de Cresson on continuous DBPs. And the idea, the way to kind of get around that is to, if you look at the kernel, the idea, the way you're going to do it is the kernel trick, right? You're going to look at this decomposition, and if you look at phi transpose phi instead, you can have sampling algorithms over a continuous space with a discrete amount of features.
Okay.
Yes.
So yeah, I was thinking that that might give you a way to do motion planning for robots, right? So we work by putting samples in a continuous space and trying to hook them up into a graph.
Right.
And there's some special algorithms that we use now to try to make them be far away from each other, but this might be another way to do it. It would be cool.
Yeah, I think, yeah, that's definitely a reasonable idea. People have actually started kind of adding ad hoc diversity in trajectory planning already. And the paper I'm thinking about, I think, is an RL paper. Diversity is all you need, that's a catchy title. And the idea is that they have a cost function that increases the diversity of the exploration term as well. And one natural way of doing this is with this log determinant, actually, that shows up as determinant of one processes. Yeah.
Thanks for the great talk. And I want to ask if P is going to be dependent on the kernel you want to approximate, and do you need to find that?
So for strongly exponentiated SR measures, yes, if you want to actually learn a model, if you want to learn an ESR to approach this problem, there's two things you need to do. First, you need to learn your SR measure, and you need to learn P as well. We haven't really looked into how to do this, although a natural way would be something like an EM algorithm. What's nice is if you actually look at the optimization problem only in terms of learning P itself, it is complex. So you can do so efficiently, but we haven't actually tried to do so in practice. Yeah.
Can you say definitively either way whether there are DPPs that, when exponentiated, can still be expressed as
Yes.
DPPs?
That's actually the example we showed. So the way it works, so here's the thing. If you actually go into, when I was talking about the definition of non-trivial is somewhat difficult to get into. If you take a size 2 by 2 DPP, even its exponentiated form is actually still a DPP. You can actually show the 2 by 2 DPPs, and ESR or SR are still DPPs. So if you go to 3 by 3 kernels, you find counterexamples of this fact. But you can also find 3 by 3 kernels that if you move P a small amount, they remain SR. And so what this means is if you actually then you can build arbitrarily large kernels just by creating Kronecker products. You have them be block diagonal 3 by 3, 2 by 2 matrices. And if you move P a small amount, like close to 1 but not equal to 1, you still have strongly Rayleigh properties. Yeah.
When you were talking about creating diverse batches, you were creating the batches sequentially in terms of the element that you add, but could you create the batches in parallel using the network?
Were you using the network? So no, you would technically still have to use K steps to generate the current architecture.
Yeah.
But yes.
But could you generate many of them?
Yes, you can do many of them if you're generating batches. Yeah. So we actually looked at this experimentally as well, and that just blows all other baselines out of the water because we can do neural networks in parallel very efficiently compared to other methods.
And could you somehow guarantee that an element is not in more than one batch doing so, or that's harder?
I haven't thought of it. That without communicating in parallel, that would be very difficult, obviously. You can guarantee that it's in none of the batches. That's easy to do. And actually, I didn't really talk about this, but if you look at our sampling algorithm, the reason that it's easy to do is because Right. If you want to guarantee that an element's not in the batch, you can actually initialize the sampling procedure not with the empty set, but with the singleton you don't want to sample. And so it will never be selected as you go, and you just remove it at the end. And you still have a diverse set, but it's also going to be diverse with respect to the elements you started with that you don't want to include. So this you can do very efficiently. And that's another advantage actually of our model.
Are there any more assumptions hiding behind the results that if you get the probabilities approximately close enough that the result is largely modular? Like say that all the probabilities are distinct?
So all we need is, let me think about this. The assumption, the only assumption we need is that we need the DPP we start with to be strictly lox modular.
Okay.
So except for, we want the inequality that characterizes lox modularity to be strict except on the evidence basically. And that's the only thing.
Any other question? Or we have people waiting for food or whatever? Well, if you don't have more questions, then we thank Sarla for the presentation. And actually, I'll just note, I remembered one thing. There are universities in other countries where you don't clap at the fences. But here we do. So I think with that, I'd like to ask the audience to exit. So